Hello everyone, welcome to week 6 of chemistry tutoring for 222. We will be going over chapter 11 today from your textbook, as well as going over colligative properties and equations with molarities, pressure, temperature, that sort of thing. So let's jump right into it. So we will be working on question 42 to start out with. Let me show you my screen. There we go. Awesome. So, question 42 says, how does 1 mole of sodium chloride depress the freezing point of 1 kilogram of water almost twice as much as 1 mole of glycerin? Okay, so for colligative properties, it is fully dependent on the amount of dissolved particles. And so because it is fully dependent on the dissolved particles, because sodium chloride is ionic and it dissolves into its ions in water, it's just ionic, period, and is aqueous, so, sodium is by itself, chloride is by itself in their ion form. And then for glycerin is not a compound that will be in a ion form at all, so it will not, it can dissolve in things, but it can only be of that compound, so it doesn't have more particles than that one compound. And so because sodium and chloride, there's two things that are dissolving versus glycerin, it'll do it twice as much, because sodium goes like this, right? There's two ions, and then the glycerin, which is just one compound, equals one compound. So the 2 is bigger than 1, and so it's twice as much because it's dependent on the amount of dissolved particles. Okay, so let's move on with knowing how colligative properties kind of work. Let's go on to 44. So this one asks, assuming ideal solution behavior, what is the boiling point of a solution of 9.04 grams of iodine gas and 75.5 grams of benzene, assuming the iodine gas is non-volatile? So, what we first have to do is outline the steps to answer this question. So, we're working with the iodine gas, we're working with benzene. It's giving us a mass of the solution as well as the mass of the benzene. And it's asking for the boiling point. So we will be using the equation delta T, so the change in temperature of the boiling point, equals Kb, which is a constant, multiplied by molality. And so this is not molarity, this is molality, and this will be the moles of solute divided by the kilograms of solvent. So this is the equation that we're working from. So we first, from the problem, it gives us the mass of the iodine gas, and so we will need to convert that to moles. So we need to first convert grams of I2 to moles. So that is our first step. Our second step is to convert the grams of the benzene to kilograms, because the benzene is the solvent in this case, and the solute is going to be the I2. So we need to find the molality. So we need to find the moles of the solute and the kilograms of the solvent. So we need to convert the grams of benzene to kilograms. And so using that, we can calculate the molality. And then for 4, using the molality, then we can find the change in the temperature of the boiling point. So multiply Kb, which is the constant like I was saying, multiplied by KB and M to find change in TB. And then we can add it to, subtract it from the original. Add. Add the change in temp to the original boiling point. So those are all of the steps we will need to find the solution to this problem. So now let's do all of those steps now. Okay, so our first step was to convert the grams of the iodine gas to moles. So it gave the mass in the question, and that was 9.04 grams of I2. And then using the molar mass, we can convert it, which is 253.8089 grams per 1 mole. And so we'll get 0.035617 moles of I2. And then our second step was to convert grams to kilograms of the benzene. And so that's just a simple conversion of 75.5 grams that it gave in the problem to kilograms, so just dividing by 1,000. And so that'll give us 0.0755 kilograms of the benzene. So now we have all we need to calculate for the molality. So let's move over here. So the molality equals the 0.035617 moles of the solute, which is I2, divided by the kilograms of solvent, which is the 0.0755 that we just found. And so dividing that out will give us a molality of 0.47175 moles per, let me move this over, moles per kilogram. And so now we have the molality and now we need to multiply it by the constant KB. And the KB in this case will be the KB of the benzene, so whatever it's going to be dissolved in, so it's going to be the solvent will be the KB value that you're finding. So the KB is just a constant value, like I said, so you don't need to calculate it. It is 2.53 degrees Celsius per molality, so that's the value that we will use. And so now all we have to do is plug this into the equation, and it's the KB multiplied by the molality that we just found, which is the 0.47175, which will give us a change in temperature of 1.1935 degrees Celsius. So that is the change in the boiling temperature. So now all we have to do is just add that to whatever benzene when it usually boils. So let's write that down. So the boiling point, or the new boiling point, will be the original, which is 80.1 degrees Celsius, and you'll also be given that too. You don't have to figure that out. Plus the change, so that's the value that we just found. Oopsie. Degrees Celsius, and so we will get a new boiling point of 81.3 degrees Celsius. So that is how we solve this problem. I usually like to take it step by step, obviously because we found the steps, but figuring out exactly the values you need first and then kind of put them all together, that's the way that I go about solving these kinds of problems, and it comes more naturally to me. But you can also, change it where you work with the equations first and then you plug stuff in. That works too. But let's move on to the next problem. Let me know if you have any questions too. This is question 45. It asks, assuming ideal solution behavior, what is the freezing temperature of a solution of 115 grams of sucrose, C12H22O11, and 350 grams of water? Outline the steps necessary to answer the question. So this is very similar to the last problem, but instead of a boiling temperature, we're working on a freezing temperature. So it's going to be still the same equation, but just with different meanings behind it. So instead of boiling, change in boiling temperature, it's going to be change in freezing. So it's going to be delta TF equals KF times the molality. So it's the same equation that we're working with. And so now let's write down what we need to do. So we have to find the molality. So just as we already covered, we need the moles of the solute. So the solute in this case will be the sucrose. The solvent will be water. And so we have the grams of sucrose, so we'll need to convert the grams of sucrose to moles. And then number 2, we need to convert grams of water to kilograms. And then once we have those two, then we can calculate the molality. And then finally, all we have to do is plug it into the equation that we just wrote out here. Plug KF and M into equation to find delta TF. And then we have to subtract the change in temperature that we just found from the original freezing temperature. So subtract delta TF from original freezing temperature. Okay, so now all we have to do is just do all of those steps. So let's start with step 1. So we need to convert the grams of sucrose to moles. So we started with 115.0 grams. And if you still need that, I'll leave those steps up here so you can look at that still if you need that. There you go. So we need to convert the grams of sucrose, so 115 grams from the problem of sucrose. And the molar mass of this is going to be 1 mole is equal to 342.30 grams, which will give us 0.335963 moles. Oop. There we go. And so now we completed step 1. Step 2 was to convert grams to kilograms of water. So we had 350 grams given to us from the problem. And so we divide by 1,000 and we will get 0.350 kilograms of water. This was sucrose. Now we have to convert the molality in step 3. So the molality, M, will equal to the moles of the solute, which is sucrose, 0.35963 was what we just got, divided by the kilograms of the solvent, which was 0.350 kilograms. And so that will give us a molality of 0.95989. I carry a lot of decimal points so that there are no rounding issues, but you could probably stop at 5 decimal places. I just need to, but that's just the way I like to calculate these. But so now that we have the molality, we'll multiply that by the KF value, which is 1.86 degrees Celsius per molality, and that is the KF value for water because this is the solvent in this situation. So let's multiply those out to find the change in temperature. So change in temperature will equal to 1.86 times the molality, 89, and that will give us a value of 1.7854. And so the new boiling point, or sorry, not boiling point, freezing point will be the difference in this. So the original freezing point of water is 0 degrees Celsius. So the new freezing point will be 0 minus 1.7854. And so that will get us a value of negative 1.7854 degrees Celsius. And since we're working with 4 significant figures, I'm going to get rid of that 4. So that is the new freezing point. Let me know if any of this doesn't make sense. But other than that, let's move on to question 47. And I'll leave that up if you're still looking at it. So 47 says, assuming ideal solution behavior, what is the osmotic pressure of an aqueous solution of 1.64 grams of calcium, I believe NO3, in water at 25 degrees Celsius? The volume of the solution is 275 milliliters. Outline the steps necessary to answer the question. So just as we did in the last 2 problems, let's write down what we need to do. So first of all, it's asking for the osmotic pressure. So we have an equation of that. And the equation for finding the osmotic pressure is going to be this fun symbol. It kind of looks like pi, but to me it looks like pi but with feet. Equal to the molarity, so capital M in this situation, multiplied by R, that's a constant, multiplied by temperature, and that's going to be in degrees Kelvin. So Kelvin, constant, and capital M is molarity. It's easy to get tricked up on molarity versus molality, and so I always like to figure out what I'm working with in the beginning so I don't continue making that mistake. So the first thing that we need to do, or one of the first things that we can do, is find the molarity. So it gives us the grams of the solute in this case, and the solvent is going to be water, and it gives us the volume of water and the mass of the solute. So what we need to do first is find the moles, or let's continue with how we said this, convert grams of, I'm going to say solute, to moles. And then number 2, it gave us milliliters of the, not of water, the solution. So molarity is, grams of solute divided by liters of solution. So we need to convert milliliters solution to liters. And then number 3, we can calculate the molarity. Calculate M. And then number 4, we need to multiply. Actually, we need to convert the Celsius first. So convert Celsius T to Kelvin. And now we can multiply M, R, which is equal to the constant, and T to find the osmotic pressure. So those are all the steps. So let's get started on finding them. So just to start out with, I'm going to write down that the R value is equal to 0.08206, and this is in pressure units of atmospheres, so using this R value will give us the pressure unit of atmospheres once we find the osmotic pressure. So now let's answer the question. How do I get back? There we go. Okay, so number 1, we need to convert to moles. And so we had 1.64 grams. I'm in the wrong color. 1.64 grams of the CaNO3, 2 moles, and the molar mass of that is going to be 164.09 grams per 1 mole. And so multiplying that out will give us a value of 0.0099945 moles. And number 2, we need to convert the milliliters of the solution to liters. So we had 275 milliliters in the problem, and we need to divide by 1,000 to convert it into liters, and that'll give us 0.275 or 275 liters of solution. There we go. So now we can calculate the molarity. So let's divide that. So molarity will equal to the moles that we just found divided by the 0.275. Which will give us a value of 0.03634,369 moles per liter. And so now we have the molarity, and step number 4, we set to convert Celsius to Kelvin, and the conversion from Celsius to Kelvin is going to be the 25 that we had, so it'll be 25 degrees Celsius, and so all we have to do is add 273.15, and that will give us the conversion to Kelvin. And so now in units of Kelvin, it will be 298.15. Looks like we found all of the variables that we needed to calculate the pressure for, so all we need to do is plug all of those in. So the osmotic pressure will be equal to the, first of all, the molarity that we just found, which was the 0.03634,369, multiplied by the R value, or the R constant, and that was the 0.08206, and then finally multiplied by the temperature, 298.15. And so the final pressure will be a value of or actually before we do that, what the answer will be before we do anything else, this will be 0.889, but because there are ions in this solution, before you circle your final answer, you have to think about what you're working with here. So because the calcium and NO3 is going to be aqueous and in its ionic form in this solution, whatever your final answer will be, you have to multiply it then by how many particles you're working with. So if it is a particle like the glycerin that we talked about earlier, since it is not in ions in the solution, it's going to be only one thing. So you'd only need to multiply it by 1. But because the CaNO3 too it has actually 3 ions in its compound here, and it's aqueous, we will need to multiply it by, is it 3? I believe it's 4. It might be just 3. We will need to multiply it by that to account for the fact that it has dissolved particles in its solution. So we will multiply it by, I have 4, and that is the correct answer, so we will have 4 ions, and because of that we will get a final answer of 2.67. Okay, there we go. And so now let's move on to the next problem. And let me know if you need that work shown. I will for a little bit while we go over the question. So number 50 says a sample of an organic compound, a non-electrolyte, weighing 1.35 grams, lowered the freezing point of 10 grams of benzene by 3.66 degrees Celsius. Assuming ideal solution behavior, calculate the molar mass of the compound. Okay, so we will be working with the same equation that we worked with finding the change in temperature. So let's write that first down. So we'll be using the change in temperature, and this is working with the freezing point. So it's going to be the change in the freezing point multiplied by Kf times the molality. And so using this equation, It's asking for the molar mass of the compound. So we will need to find the molality first, and so that will give us grams of the solute divided by the kilograms of the solvent. And because benzene, where is it here? So it's an organic compound, and so benzene is going to be the solvent here, and because we can we can divide by it, we can isolate exactly the molar mass of this compound. And so I'll show you what that looks like. So let's first move some things around. So M will be equal to the change in TF divided by KF. And so the change in temperature was the 3.66, and the KF value is going to be 5.12. And so finding the molality, it is equal to 0.71484375. And because this is in moles per kilogram, and so it's moles of solute divided by kilograms of solvent, the solvent in this situation is going to be the benzene. And so because it's the benzene, we can find the moles of solute if we multiply the value that we just found multiplied by the 10 grams of the benzene to isolate to get to moles. But we will need to convert the grams to kilograms, so let's just do that conversion. So there's 1,000 grams for every 1 kilogram. So that is how we isolate to moles. And so now when we calculate this out, we will get a value of 0.007148 moles. And because in the problem it said the moles of the unknown compound, or sorry, it said the grams of the unknown compound, the molar mass is equal to grams per mole. So using the grams that we had in the problem, or were given, was 1.35 divided by the moles that we just found, 438, will give us a molar mass of 188.9 grams per mole. So that is how we solve this problem. Okay, and let us move on to the next problem. So 52 asks, a solution contains 5 grams of urea, CONH2, a non-volatile compound dissolved in 0.100 kilograms of water. If the vapor pressure of pure water at 25 degrees Celsius is 23.7 torr, what is the vapor pressure of the solution? So this is assuming ideal solution behavior, and we have an equation for this problem. So the equation for finding the, I believe it is asking for the vapor pressure. To find the vapor pressure, we need to use the equation P of solution, so that's the pressure of the solution, is equal to the mole ratio of the solvent multiplied by the pressure of the solvent. And so we can first find the X here, which is the mole ratio. And so mole ratio is going to be, or sorry, not mole ratio, mole fraction, is going to be the moles of the solute, or since we're working with solvent, the moles of the solvent divided by total moles. So this will equal moles of solvent divided by total moles. And so we can first find this variable here. And so again, it is asking for the vapor pressure of the solution. So once we find the mole fraction, now we have to plug in the pressure of the solvent, which it already gave us in the problem, which is going to be the 23.7 torr and that's the water, right? Because the water in here it's usually is the solvent, but the water is the solvent here, and then the compound that is the urea is going to be the solute. So all we have to do is really just find the mole fraction and then multiply it by the P solvent, and we already have that. So to find the moles of solvent and the total moles, we need to convert the mass of water and also the urea into moles. So let's first do the urea. So it gave us, in the problem, it said we have 5 grams of urea. And so the molar mass of that is going to be the 60.06 grams. And so that will give us a mole amount of 0.0832500083 moles of urea. And now that we have the moles of the urea, we need to find the moles of the water. And it also gave us a mass of that, which was the 0.100 kilograms of water. And so now let's convert to grams and then to moles. So for every 1 kilogram, there is 1,000 grams. And for 18.02 grams, there is 1 mole of water. So we will get a mole amount of 5.54939 moles of water. Okay, so now that we have moles of urea and moles of water, we can calculate for the mole fraction of the solvent. And again, the formula for that is going to be right here. X solvent will be moles of solvent divided by total moles. And so the moles of the solvent is going to be the water. And so that was the 5.54439 that we just found. And so the total moles will be the moles of urea plus the moles of the water. Nope, plus. And so that will be the fraction. And so now that we have the mole fraction, we can just directly implement this into finding the P of the solvent, so the pressure of the water. So I'm just going to carry that down. Actually, no, I'm going to multiply that before, so it's a little bit cleaner. 5.4439 divided by the total of 0.0832500083 plus 5.4439. So that'll give us a value of 1.003119133. And so since we have the X solvent, we need to multiply by the pressure of the solvent as well. Oh, sorry. We're finding the solution here. And so from the problem, it gave us 23.7 torr of the pressure of the solvent. So multiplying that out will give us a value of 23.58205049. There we go. And rounding that to 3 significant figures, we will get a value of 23.6 torr. So that is going to be the vapor pressure of the solution. Awesome. So let's move on to question 54. So question 54 is going to ask us to rank the decreasing freezing points of 0.1 molality of the Na3PO4, 0.1 molality of C2H5OH, 0.01 molality of CO2, 0.15 molality of sodium chloride, and 0.2 molality of calcium chloride. So how we go about solving this is very similar to how we define the colligative property, and that is on the basis of the dissolved particles in the solution will account to how well it is able to depress the freezing point. And because if there's more ions in the solution, more particles, it is going to have a higher change in that temperature, and so it's going to do a better job at freezing the solution. So given each of these compounds here, we can multiply the molality it gives us, so the 0.1, the 0.1 here, 0.01, 0.15, and 0.2, multiply it by the ions and how many particles respectively to each one of those molalities, and so then we'll be able to figure out which one is highest, and the higher value that it gives us will be the higher amount that it decreases its freezing point. So let me give you an example of how to go about doing that. So the Na3 PO4 is going to be in ionic form, and so going into its ions, we will have 3 sodiums and then 1 of the PO4 here, and so that will give us a total of 4 ions. And so because it has 4 ions, we need to multiply it by this 0.1, and so we will get 0.4. So it'll do a pretty good job of decreasing its freezing point. Now let's move on to the next one here, which is the H5OH, or sorry, C2H5OH. So C2H5OH. This is not going to be in any ions in the solution, so it'll just have 1 particle. And so because of that, 1 particle times its molality, which was 0.1, will give us just 0.1. Okay, now let's move on to the next one, which is CO2. CO2, it's also the same way. It is going to be 1 particle. It's not going to dissolve in ions. And so multiplying it by the 0.01 it gave us, we will get a value of 0.01. And so now let's move on to the next one. So sodium chloride. Sodium chloride does have ions in its solution. So of the NaCl, it is going to be going to Na and Cl. If you want to write down the charges, you can. Oh, yes, Fruny. How do you know if something is ionic when looking at the compound? Is there a general rule? Yes, so when I was taking this class a while ago, there was a sheet that we had to look at if it was soluble and if it combined with certain things. Like it would say sodium if combined, or sodium if it combined with these things, it would be solid. But other than that, it would be aqueous in a ionic solution. And oftentimes when you have a carbon and hydrogen and oxygen, so the C2H5OH here, it's not typically going to be in ionic form. Same with the CO2. And also besides that sheet, if you don't have that, when looking at the actual compound, like we see the NaCl here, the sodium is a metal and the chlorine is not. So this is a ionic compound in itself. Same with the CaCl2. So if you know that these two things are ionic, then you can look at if the solubility rules of like the sheet, for example. Because the CO2, this is not ionic because it's carbon and oxygen. It's non-metal only. And the sodium chloride and the CaCl2, that's a metal and a non-metal, so it is ionic. But some ionic compounds don't necessarily are ions in solution. So you need to look up the rules with solubility. So if that makes sense at all. Okay, so other than that, let's move on to finishing this one. So because yeah, awesome, great. Yeah, because the sodium chloride is an ion compound, the sodium and the chloride will have two particles. So 2 particles times the molality that it gave us, which is 0.15. And so that'll give us a value of 0.3. And so lastly, let's look at the CaCl2, and that is a ionic compound. And so that'll dissolve into 3 particles because of the calcium and also because of 2 of this, of the 2 of the chlorine. So that is 3 particles in total times the molality that it gave us, which was the 0.2. Let me clear that up too. There we go. And that'll give us a value of 0.6. So now that we have all of these values for each of these compounds, there's 0.4, 0.1, 0.01, 0.3, and 0.6. So these are all the values that we got. And it asks us in the problem to rank them in order by their decreasing freezing points. So because the highest is going to be the highest number that we found, which is the bottom one here, that is the highest rank. And so following that order, a little bit less than CaCl2 is going to be the Na3PO4 with a value of 0.4. And then moving from that is the sodium chloride with 0.3. And then with 0.1, we have the C2H5OH. And then following that, we have CO2. So that is the ranking of the freezing points. And I'll leave that up if you need to look at that. Okay, so the last one I believe for the day, is 61, and it says the osmotic pressure of human blood is 7.6 atmospheres at 37 degrees Celsius. What mass of glucose, C6H12O6, is required to make 1 liter of aqueous solution for intravenous feeding if the solution must have the same osmotic pressure as blood at body temperature, 37 degrees Celsius? So we are going to be using the same equation that we were finding the osmotic pressure for. So I will write that down to begin with. So we have the pi with the little feet equals the capital M molarity times the R, the constant, multiplied by T, the temperature. And so because we're trying to find the mass, again, we need to focus on this variable here, the molarity. So this is the moles of solute. And so the moles of solute in this problem is the glucose. So the moles of glucose divided by liters of the solution. So just before we move on with calculating things, because we have 1 liter of the solution, I'm going to multiply this by 1 liter, and so we will end up getting moles of glucose. So just sometimes it's easier to do that before continuing. But if we are going to try to find the mass of the glucose, let's first isolate that in the equation. So we'll have M equals the osmotic pressure divided by RT. And like I said, if you multiply it by the 1 liter, you will get, so let's put right there, you will get the moles of glucose. Actually, it's right over here. So times 1 liter, we will get 1 mole, or moles, of glucose. And so writing it again, osmotic pressure divided by R and T. And so the osmotic pressure that it gave us in this problem was 7.6. And the R constant is going to be 0.08206. And the 7.6 is in units of atmospheres. And so just make sure the R constant that you use is also in pressure units of atmospheres within it. And then we need to multiply by the temperature, and because the problem gave us Celsius, we need to convert it to Kelvin. So 37 degrees Celsius and then we need to add the 273.15 to get it into Kelvin. And so once we multiply all that out, let me calculate it. So 7.6 divided by 0.08206 times 37 plus 273.15. We'll get a value of 0.2986, 14089 moles. Okay, glucose, there we go. Okay, so now that we have moles of glucose, the problem asks us to find the mass of the glucose. So now all we have to do is multiply it by the molar mass of glucose. So let's start with the 2,986,14089 moles that we got. And using the molar mass, it is 180.16 grams for every 1 mole of glucose. Oh, sorry. Let's switch that around. The grams go on the top this time. I'm so used to the other way around. Okay, multiplying that out, we will get a mass of 53.8 grams. So that is the mass of the glucose in this problem. And I'll zoom out if you need to look at all of that as well. Okay, so that is all that I have for today. Hopefully this helped with how to figure out how to solve these kinds of problems and where to start. And hopefully these concepts are getting more ingrained. Sometimes they can be kind of tricky to think about at first, but once you get in the hang of it, it can come more natural to you. So yeah, that's the wrap on colligative properties. Let me know if you have any more questions. I'll stick around for a couple more minutes, but as always, this is going to be uploaded to the PSU Learning Center YouTube channel. So if you want to ever look at past recordings or the recording of today, it'll be posted soon. So other than that, have a great weekend, and I'll see you all next week.